Thanks, Jessica. And yeah, thank you so much for having me here. It's really exciting to be celebrating 42 years of alternating sign matrices. In my work, they have a habit of popping in to the same story in multiple different ways. So they're playing like different roles as like geometric objects, but they're also somehow like telling you how to write down polynomials that go along with these geometric objects. And the two ways that they show up is very, very different and distinct. So these are, yeah, I mean, I'm in the right room. These are some of my favorite mathematical objects. And so I want to tell you, yeah, how they show up in my Schubert calculus world. So I recognize some of you are not studying Schubert calculus in your day-to-day life. So I just wanted to do kind of the quick primer and motivation and why do we study some of the things that we study in this Schubert calculus land. If you do know the story, bear with me, but I hope it's new for many of you. Okay. So Schubert calculus, at its heart, it's asking enumerative questions about how objects sit together in space. So for instance, I can ask a warm-up question. If I fix two lines in a plane, how do they meet? And well, they meet in a point, usually. Sometimes I could take the same line, two copies of the same line, and well, that meets in a line, but that's very special. That almost never happens. Or I could take parallel lines, but basically, morally, they're kind of meeting at infinity. And this is why we really tend to, instead of looking at this affine picture that I can draw very well, we tend to projectivize and study projective spaces and projective varieties where the intersection number counts work out the way you expect. But on the whole, if you take two lines in space at random and they live in a plane, they're probably going to meet in a point. So you're like, yeah, I know this. I took geometry. But let's look at another question. So if I fix four lines at random in three space, my picture might look like it's sitting in a plane, but pretend it's three space. So if I fix these four lines, how many lines are there that meet all four of the fixed lines? So again, if you know the answer already, no cheating. But anyone, I mean, it's not cheating to know stuff already, but don't spoil it. But anyone who hasn't seen this before, have a guess. Or you're all Schubert calculus experts. It's okay to guess and be wrong. I mean, we're mathematicians. Anyone? Yeah, random fixed lines. Yeah, it kind of looks like if you're just like, you got a lot of space in free space. And if you're just like trying to shoot a line that meets all four of the fixed lines, seems like there's a lot of ways to miss it. So like zero feels like reasonable intuition. Maybe it's two. Oh, why do you think it's two? So it actually is two. Let me tell you about a way that you can think about this. And it's maybe a little bit cheating because I told you you're supposed to take four lines at random. But the idea of Hermann Schubert and his contemporaries, the Schubert calculators, what you can do is you can kind of mildly deform the situation and you expect that the number of solutions gets preserved. So what I'm going to do is I'm going to take a pair of these fixed lines and I'm going to deform them so that they intersect and take another pair and deform them so that they intersect. Now, can anyone find me any solutions? A line that hits all four of these special fixed lines. I saw Jessica go like this. I think Jessica is telling us that there's a line that passes between the two intersection points. Excellent. Is anyone teaching multivariate calc right now? No? Yeah. Well, does anyone remember multivariate calc? You didn't know you'd be getting this pop quiz at like 9:30 in the morning. What do two lines span? A plane. And if you have two planes in three space, how do you expect them to meet? In a line. So if things are like, I mean, we've made things a little bit less random, but if they're random enough, you expect that these four lines are going to, you have a line passing through the intersection point, and the line where these planes intersect is also hitting all four of the fixed lines. You have to extend the lines I drew a bit, but you can see, okay, as long as we're not like sitting parallel to this intersection line, we're going to be okay. So yeah, the answer, in fact, is two. If you have four lines in three space, you can kind of deform this picture back to your original four lines and somehow drag the solutions back and preserve this solution count. But this notion of deforming the situation, it wasn't so rigorous, and different Schubert calculators would sometimes get different answers to the same enumeration question, which wasn't so good. So Hilbert in the year 1900 proposed his big list of problems, which shaped the trajectory of mathematics for the next century and beyond. And his 15th problem was about Schubert calculus. So Hilbert said, let's make Schubert calculus rigorous and let's find ways to predict these intersection numbers. So the making things rigorous really came through the development of a lot of machinery and algebraic geometry. So things like intersection and Chow groups and or intersection theory and studying Chow groups and cohomology theories. And understanding projective spaces and algebraic varieties. And the sort of ways to predict intersection numbers is kind of the corner of Schubert calculus I tend to live in, where really a lot of the initial answers came by way of tableau combinatorics and symmetric function theory, where there's really nice ways to predict certain intersection numbers. But there's more like general spaces you can think about that are representing more general types of intersections. And there's still a lot of combinatorics to be worked out. So that's often the world that I'm living in when I'm thinking about Schubert calculus. So the idea of this make it rigorous is often that we take some space. This could be a projective space or a Grassmannian or a flag variety, which is just a nested the set of nested sequences of vector subspaces. So you can take whatever your space is. You can study some nice orbit closures that are called Schubert varieties in that space. And for the projective space, they're just indexed by numbers. For Grassmannians, they're indexed by partitions. And for the flag variety, they're indexed by permutations. And then you take these sort of distinguished orbit closures. They are giving you a basis of Schubert classes, and you do computations in the cohomology ring of this variety to understand these intersections. Sorry, I keep moving too far from the microphone. Okay. So in trying to understand these intersections, what you want to do is you want to understand products of Schubert classes in whatever this cohomology ring is. It's very easy for projective space. It's just you take these numbers indexing your classes and you add them as long as they don't get too big. Oh, I think that should be though an n plus one. No. I think I lied. Or I want a zero. I didn't have a zero when I wrote that. N plus one. Okay. Numbers 0 through n. So you just add them unless they get too big and then you get 0. So yeah, this ring is just like a very easy quotient of a polynomial ring. The Grassmannian, the rule is a bit more complicated for how to multiply, but there's a beautiful, actually many different iterations of this same Littlewood-Richardson rule where you can just put some numbers in boxes according to certain rules and count the number of such things that you can get. And this tells you your structure constants. But for the flag variety, only special cases are known for these multiplication rules. Of course, you can just multiply in some sense, and I'll talk momentarily about some polynomial representatives for these classes, but Hilbert wanted to be able to predict the numbers without doing algebraic elimination. So without having to do any linear algebra at all, to just be able to know what these structure constants are. So this is a big open problem in Schubert calculus to understand these structure constants. So good news for us, if you like me are not wanting to do cup products and cohomology rings, you can think about this ring as just a quotient of a polynomial ring. So it's just an ordinary polynomial ring in n variables, and you quotient out by this ideal that's generated by the non-constant elementary symmetric polynomials. So Lascaux and Schutzenberger, building on work of others, they gave a choice of polynomial representatives for these special Schubert classes called Schubert polynomials. And their initial definition was in terms of divided difference operators, where you start from some top special Schubert polynomial, and you get the rest by just applying these funny little sort of geometrically, they're like push-pull operators, but you just like do this thing to polynomials, which I'm not going to tell you, but it's easy to do. You can just tell a computer to do it or a student to do it, and you can start computing some Schubert polynomials. And then to understand how to multiply cohomology classes, it turns out that these Schubert polynomials, there's some sort of limit where you can think about them as being indexed by S infinity. And when you're taking products of these things, you get this basis for the polynomial ring in as many variables as you could want. And you get the same structure constants for this multiplication. So whenever you multiply two things in Sn, and you get something in Sn in this big infinite expansion, its coefficient is going to agree with what you were seeing in the flag variety. So the point of all those many words is just that you can multiply polynomials to try to understand this ring instead of doing any geometry. So that's often what I do. I think about these polynomials and associated combinatorics. So in particular, this is a conference on alternating sign matrices, and there's an alternating sign matrix formula for Schubert polynomials, due, I would say, both to Lamley-Shimizono in the formulation that I'm going to show you, but also secretly due to older work of Lascaux, where he did something a little more general. Okay. So I'm going to define this object and tell you its Schubert calculus name, but you're experts on ASM, so maybe you already recognize what object it is. But a bumpless pipe dream is just a tiling of the n by n grid with these 6 tiles, 6, what a good number, so that pipes start at the bottom of the grid and end at the right. Now, you might be like, why are they called bumpless? Well, in Schubert calculus land, often the pipe dreams that we thought about before these had these bumping tiles that I pictured below and these crossing tiles. So Lamley-Shimizono, when they came across these new to them objects, they said, okay, they're like these other pipe dreams, but now we can't have these bumps. We have different tiles involved. So these are bumpless pipe dreams. Okay. Well, this is just, it's an alternating sign matrix. And really, it's like just a hair away from an osculating lattice path. It is an osculating lattice path if you just draw the crossing as like a little osculating point instead. But what we really like about these tiles is we do actually want to think about these lattice paths as sort of passing through each other in a certain way. And from these, we'll be able to get the data of a permutation, which will let us write down our Schubert polynomials. But in this picture I've drawn, I'm just emphasizing that we can take a configuration of the 6 vertex model with domain wall boundary conditions, and we can just take the arrows that point left and down and draw those and forget about the rest of the picture. And of course, this is enough to uniquely identify which configuration of the 6 vertex model that we had, just by this tile by tile, vertex by vertex map that I'm showing you. And the rules about where pipes start and end, that's just the domain wall boundary conditions. Questions? Yeah. So I'll tell you momentarily how to read a permutation off. And we really do want to think about the pipes as crossing each other, because if I drew a bump, then I would just send those pipes on their way. Yeah. So it's mainly the way we're reading a permutation, but they are transparently the same objects. Yeah. Just in Schubert calculus land, we were a little late to osculating lattice paths. Okay. And then, of course, we can go directly to an alternating sign matrix by making these tile by tile replacements, which are just the same ones you would do with the 6 vertex model. Okay. So we need an extra definition, and this is, again, where the crossings kind of come into play. We say that a bumpless pipe dream is reduced if pairwise its pipes cross at most one time. So to really emphasize this definition, it was easier for me to draw a non-reduced, a non-example. This is the only one out of the 42 4x4 bumpless pipe dreams that fails to be reduced. So this is kind of the smallest non-example I can give you. But the point is that as we follow along these pipes, as we follow along these pipes, we cross here and cross here. And so those two pipes came back and crossed each other again. So when we take just the reduced pipe dreams, we're able to write down Schubert polynomials. So what we do to get a permutation in this case is we just follow the pipes. So here I can kind of draw along, and now here we go. So I can follow this one, and it pops out up here. And I follow this 2, goes out there, this 3, this 4, and this 5. And so to this object, I associate the permutation 1, 4, 3, 2, 5. So I just trace out the pipes along that. And then I also associated a weight. So for bumpless pipe dreams, what's important is the positions of the blank tiles. And we just look what row are they sitting in, and we associate to them an xi. So this is similar to what was going on before in terms of putting weights on 6 vertex model configurations, but now we're just doing different weights from what we saw yesterday. So then the theorem of Lamley-Chamizono is that the Schubert polynomial is a weighted sum over reduced bumpless pipe dreams for your fixed permutation. So now, even though I didn't give you the divided difference operator, you have all the tools you need to be able to write down one of these Schubert polynomials. And I've done a small example for you here, 2, 1, 4, 3. For these bumpless pipe dreams, there's a lot that I'm not telling you about, like, okay, in practice, how do I figure out how to draw these pipes so that I get all the right ones to trace out the permutation I'm looking for? But there's these nice droop moves that let you kind of take a pipe and drag it sort of downwards and into blank spaces. And so you can kind of keep drooping and drooping in some sort of way and generate all these pictures. So they're fairly nice to work with in that sense. But questions? Okay. I want to tell you a little bit about these other objects that aren't really ASM objects, but they're sort of the original, they are the original pipe dreams that people studied in Schubert calculus. So again, there's certain tilings where we have certain rules. And on the main antidiagonal, we have just sort of these bumps. Below the main antidiagonal, we just have this blank space. And then above the main antidiagonal, we can kind of freely put in crosses or bumps. And we just read off a permutation again by sort of following the pipes. And here we get 4, 2, 6, 1, 3, 5. And the weight is a little different this time because, well, they all have the same set of blank tiles. That would not be an interesting weight for these objects. Instead, we weight things by looking at where the crossings are. So again, they feel similar in that we're drawing these squiggles and we're following the squiggles to get a permutation, but they're just different objects. So the theorem, I'm putting a few names. Really, I could put a lot of names, various guises of this written in various formulations, but the theorem of Fomin-Krylov and Bergeron-Billy really put them in this grid sort of format. Is that the Schubert polynomial is a weighted sum over reduced pipe dreams for W. So reduced again in the same sense that pairwise pipes cross at most once. And well, here I've written down these 3 objects, and if you remember the weights from before, they line up. And indeed, I'm not going to make you remember. Looking at these, we can compare formulas, and there's a weight preserving bijection due to Gao and Huang that really lets you say, well, in this example, you had no choice. So I lined them up the only way we could to preserve the monomial weights. But in general, you could have many objects give you the same monomial for a fixed permutation. And Gao and Huang give a very nice way to compare these. And their bijection is canonical in the sense that if you have a bijection that respects certain multiplication rules for Schubert polynomials, then any of these bijections are actually the same bijection. So there's not much choice if you want a multiplication preserving bijection. Okay, so there's some sort of connection here between these bumpless pipe dreams and the ordinary ones. Now, there's also a version where we don't just track row information, but we also track column information. These are called double Schubert polynomials, so we have double the variables now. And these, there is no way to just, in general, if you have a fixed permutation, line up a pipe dream and a bumpless pipe dream and preserve this X and Y weight simultaneously. So there's something a bit more structure and or something a bit different about these structures. And you start to see that these two different objects have different behavior, but still somehow give you the same polynomial. There are, again, combinatorial explanations for like of Udall and Knudsen of how to kind of toggle between bumpless pipe dreams and pipe dreams and take the Y weights along for the ride. But it's a bit more subtle than just sort of lining things up monomial by monomial. You have to make like auxiliary objects in some sense and then line those up. But anyways, this is just to highlight some similarities and differences between these two ways of writing down Schubert polynomials. So now what I'm going to do is tell you about a K-theoretic generalization of Schubert polynomials called Grothendieck polynomials. Yes. Uh-huh. Yeah. 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 But now I'm going to stop throwing away the ASMs and everyone will contribute. Yeah. So in K theory, it's much more natural from the ASM perspective. Everything gets used. Yeah. Okay. Yeah. Mhm. Oh, a poset structure. Oh, yes. So there's, yeah. So for vexillary bumpless pipe dreams, it's a lattice. But then for other ones, like the natural sort of droop moves and the K-theoretic generalizations of droops, you always start from some initial diagram and then you're working your way towards lots of diagrams. So I don't like, I mean, it's not a lattice, but maybe there's a different thing you could do. Yeah. Yeah. But that was your nice conjecture about the lattice structure on, oh no, sorry, on pipe dreams. No, never mind. Oh, okay, I'll keep going. So, Grothendieck polynomials. So Grothendieck polynomials, we're going to use all of the alternating sign matrices now, but we're still going to group them by permutations in a certain way. So I told you before we needed pipes to cross. What's that? Oh, okay. We need pipes to cross at most once to make sense of this permutation. And I just told you that because we're just getting used to these objects, but now you're experts, so you can handle things crossing more than once. But we have to read in a more subtle way if we have multiple crossings. And so we kind of follow along these pipes. And like here, they haven't crossed yet, so we're not in any danger. But at this point, these two pipes have already crossed, and we only allow things to cross once. And so I say, okay, you're not allowed to cross through each other. Instead, you have to bump. And then I read the pipes in that sort of way. So that's why I really do get a 2-1 instead of the 1-2 that you might naively expect if you just read sort of passing through crossings in the normal way. So it's a little more subtle way to read the pipes. But this is really the translation that I gave of an older formula of Lascaux, where he wrote a formula for Grothendieck polynomials as sums over literal alternating sign matrices. So if you know this paper, Chern and Yang through ice, what Lascaux did there was he introduced this thing called inflation on ASMs, which was a way to iteratively get rid of the -1s until you find yourself at a permutation matrix. And he called this permutation the key of the alternating sign matrix. So this funny way of reading permutations along pipes, I showed is the same permutation as Lascaux's key. So if you would rather not do inflation and would rather get your permutation by following these pipes, you can do so now. The weight is also a little bit more complicated and a little funny. We have sort of this sign which says, let's take the number of blank tiles minus the Coxeter length of the permutation. And then we're going to take a product over these blank tiles, and those get the same usual weight. But then there's some extra K-theoretic stuff where whenever we have these upward bumps, we get a 1 minus xi for each of those upward bumps. So this is our K-theoretic weight, but then the theorem looks very similar, that you get the Grothendieck polynomial by summing over the bumpless pipe dreams that trace out that permutation with these appropriate K-theoretic weights. So one feature of Grothendieck polynomials is that they happen to alternate, their monomials alternate in sign with degree. So this funny extra weight that I had to do was really just taking these sort of these had just 2 blank tiles and these were the reduced objects, but this non-reduced object got an extra blank tile. So I just had to modify the parity there. But anyways, this is the formula for Grothendieck polynomials. Questions? Okay, so now what we're gonna do is I'm gonna tell you about how we can 2-enumerate ASMs with this. It's a little bit silly because there's many nice proofs of 2-enumeration of ASMs. And this one is kind of like, oh, if I have all this machinery, then I can just give a very fast proof by comparing 2 formulas for Grothendieck polynomials. But I just want to tell you that there is this Schubert calculus proof. I think Lascaux knew of it. He has a lot of preprints where he writes a lot of things. And so I think it's basically in one of his preprints. Yeah. So what we do is we can make this specialization into our Grothendieck polynomial. We can send each xi to -1, and we can multiply the whole Grothendieck polynomial by -1 to the Coxeter length of w. And this is going to give us our 2-enumeration weight. So we get just 2 to the number of -1s when we make this specialization into this monomial. So we can do that in our Grothendieck formula with bumpless pipe dreams, but there's also a formula with just pipe dreams. And pipe dreams, again, we're taking these different fillings, but now we can allow multiple crossings and we have some sort of funny sign, so things alternate with degree. But what's going on is the n by n pipe dreams, they're in bijections with this subset of the grid, just based off of where did I put my crossing tiles. In other words, there's 2 to the n choose 2 pipe dreams. And each of those is contributing 1 when we're summing up all our Grothendieck polynomials in this sort of funny specialized way with this twist to make the signs work out right. So our sum over pipe dreams is the same as our 2-enumeration sum of ASMs. So this proves the 2-enumeration formula. Again, by maybe going a bit overkill with we have to have some sort of theory of Grothendieck polynomials and prove 2 different formulas for Grothendieck polynomials. But yeah, it's kind of fun. Here I've just written out for 3x3s all of our 8 different pipe. Oh wait, sorry. We have, yes, 8 7, 2, 4, I can count, 6, 8. 8 different pipe dreams. It should have been a power of 2. It's maybe 3 a.m. in my normal time zone. I'll just keep using that excuse. But anyways, this 2-enumeration, most of them are just permutation matrices, and we have this one that has a -1 that's contributing a 2. Okay. All right, so that was sort of the first portion of how ASMs show up in Schubert calculus world. And now I'm going to tell you a bit more of a geometric story where each of these ASMs is indexing some sort of object that's a generalization of what's called a determinantal variety. And again, I want to start with just a little bit of a warm-up to get us into this world. And so there's a lot of nice group actions on affine space. So we can just take some number of copies of whatever affine space we want, but usually I'll just use C because it's nice. So we can act by this group C star where we have the complex numbers, but we take away 0 and it's a group under multiplication. And we can act just by scaling. And so the scaling action, it has kind of, we want to look at its orbits of the action. And we have one special orbit where if we start with the 0 vector, we're just going to always get 0 if we try to rescale it. But then the rest of the orbits, when we look at this equivalence relation of the things we can get to from one another by scaling, these just look like points in projective space. So here's a nice warm-up group action that is something that's familiar. There's another nice group action on affine space. We can act by 2 copies of our general linear group, so the group of invertible matrices, on the space of m by n matrices by change of basis. And we can ask ourselves, okay, if I'm doing this action, what are my orbits? And again, it's time for the pop quiz portion of today. If I take a matrix and I rescale it on either side by an invertible matrix, like what form can I bring it into? Yeah, just reduced row echelon form. And so it really comes down to like how many ones are there in this reduced row echelon form, which is also known as rank. So these orbits really just get classified by the rank of the matrix, which again, how natural is that? Like that's just a very, very natural condition. So this action preserves rank, and indeed, 2 things have the same rank if and only if they're in the same orbit. Okay. So we can also look at these orbits and we can think about orbit closures. So I mean this in the sense of like Zariski topology, and it gets a bit more subtle, but I'm just going to tell you that combinatorially, what orbit closure looks like here is instead of saying, let's look at this orbit that has matrices of rank exactly R, I can look at the matrices of rank at most R. And that's what the closure looks like. And these closures are classical determinantal varieties. And why determinant? Well, this rank at the T didn't go along with yeah. But what's going on here is if we specify that we have something rank at most a number, well, that's equivalent to saying if I look at all the R+1 size matrix minors, they vanish. So again, this is an exercise in linear algebra to show this. So for instance, if I have this matrix here, and I want to make sure that it's rank at most 1, I need all of its 2 by 2 minors to be 0. So that's why they're determinantal varieties, because we're carving them out by determinantal conditions. If I had rank at most 0, well, I need the 0 matrix. So all those 1 by 1 minors vanish. Rank at most 2, well, there's no valid 3 by 3 minors. I'm just placing no condition. And that makes sense because, well, the biggest rank a 2 by 3 matrix can be is 2. So these are very nice objects. They're often a testing ground in algebraic geometry and commutative algebra to try to prove things about these before you take on harder spaces. But let's look at one more example, and this is the one that's most relevant to our Schubert calculus world. It's a generalization of these determinantal varieties. What we do is instead of acting by GLM cross GLN, we act by, so I have a little bit of notation here. This B minus, it's B for Borel subgroup, which the minus, we're just saying, let's take the lower triangular invertible matrices. And this B of n, we're saying, let's take n by n upper triangular matrices. And let's act on our matrix space, again, by this sort of base change action. And the idea, really, what this action is saying is that if I take my matrix and I want to start doing like linear algebra operations, I can do row operations that sweep down. So I can take copies of a row and I can add them to lower rows. And I can do column operations that sweep right. So I can take a copy of a column and add it to a later column. So with these slightly more restrictive row operations, you can see that matrices are in the same orbit if and only if they have this same rank matrix, where what we're doing is for each ij, we're recording the rank of the submatrix that starts at position 1, 1, and has lower corner at position ij. So take the first I rows and j columns. And you can see right away that these rank matrices are preserved because of how I've described the sweeping of the row and column operations. If I take a copy of a thing and I add it to a later thing, it's not going to mess up the rank of anything before that. But it could, if I went the other way, that could mess things up. So again, this is just a thing you can check with linear algebra. And here I've written down a couple of matrices that have the same rank table. And so I claim that they're in the same orbit. And it gets better than that. It turns out that orbits are indexed by partial permutation matrices, where we can have zeros and ones as our entry, and then we have at most one in each row and column. So yeah, for this, the orbit closures then are still a similar sort of downward inequality thing, but now we have to look at each position in our rank table to determine if one orbit is contained in another. And so these orbit closures are called matrix Schubert varieties. They were defined by Fulton in 91. So here I've drawn this sort of poset of partial permutation matrices for 2 by 2 and the corresponding rank tables. I've drawn it upside down from the orbit containment poset. And this is because, well, what I have here for permutations, this is the Bruja order on the symmetric group here. And so up to some like sort of stabilization, these partial permutations, we can interpret them as larger permutations. And we're really just getting a sub-interval in strong Bruja order of the symmetric group. And this is just something you can prove about these rank tables for permutation matrices. Questions? Okay. So because of this sort of stabilization and not having to worry so much about like which symmetric group we're living in and being able to take like a big enough one and all your partial permutations turn into permutations, it's enough for us to just focus on honest permutation matrices instead of partial permutations. So here I've drawn the 3 by 3 permutation matrices. And well, I don't know, often we like lattices. And when we look at this picture, it feels like something's kind of missing. And also this is a conference on ASMs and maybe it feels like something is missing. I've talked about permutations a long time now. So indeed, we could just like fill in an extra little element there and we would have a nice lattice in this example. And does anyone see how I could like put in a rank table that would like kind of fit in between these? You don't have to say the whole rank table, but like, yeah, you could take the minimum of these two or the maximum entry-wise of these two. And when you do that, you get this nice little matrix there. Still kind of looks like one of these rank tables where things are kind of starting on the left column and the top row, entries are 0 or 1. And then as we're reading across, we're kind of going up by at most 1. And then we want to get to sort of this boundary condition 1, 2, 3, 1, 2, 3. So it's a matrix like that, but it has this extra little sort of weird spot where essentially if we do this plus this, 1 plus 3, let's see, oh no, this plus this minus this, we're going to get sorry, I should be doing addition, definitely. Yeah, great. So I was taking determinants in my head, which is not what I want to be doing. So if I do 0 plus 1, minus 1, minus 1, what I get is a minus 1. So there's some sort of like boundary conditions of zeros, but this is like an invertible map taking, instead of ranks, taking these things called corner sums. And what was missing in the middle was really our alternating sign matrix. That's not a permutation matrix. So this was, yeah, the theorem of Lascaux and Schutz and Berger. And sorry, this title, I think I wanted poset of alternating sign matrices, but the varieties are coming. But the theorem of Lascaux and Schutz and Berger is that alternating sign matrices ordered by these corner sum matrices, where instead of taking ranks, you just really sum up all the entries in some fixed maximal submatrix. They form the Dedekind-McNeil completion of the strong Bruja order on the symmetric group. So it's sort of the smallest lattice that contains this poset as a subposet. So it's the most efficient way to embed the strong Bruja order as a lattice. So here, this corner sum, I'm literally just taking, to get this one, I'm taking the sum of these entries. And I do that for every different entry to get this. When I have rank matrices of permutations, permutation matrices are so simple that I really am just taking corner sums to compute those ranks. Okay, so what we can do is we can take these corner sums now and we can use them to define a geometric object, like what we did with our matrix Schubert varieties, which were carved out by a bunch of different rank conditions. So we can just replace our specified list of rank conditions with the ranks coming from our corner sum matrix. So here, for instance, I can take kind of a generic looking matrix B, and I'm going to declare that, okay, this is something living in my variety XA. And because this rank of this top corner has to be 0, I need B11 to be 0. In other words, I need that 1 by 1 minor to vanish. And then here, I want this submatrix to be rank at most 1. And so I need this minor to vanish. I already made B11 vanish, so I could just substitute that in and then take this determinant. And then this really tells me that, okay, I need B12 to be 0 or B21 to be 0. So this thing is no longer like a nice irreducible variety like these orbit closures were, these matrix Schubert varieties. Fulton actually told us that these things are irreducible for like any choice of rank table, if and only if your rank table is arising from some permutation matrix. But we can write down what their components are without too much strife, but we have to kind of go searching in our poset of ASMs. So we can let perm of A be the sort of permutations that are minimally above your fixed ASM. So if you're a permutation, your perm set is just yourself. And then this XA is the union over the sort of matrix Schubert varieties that are minimally, their permutations are minimally above. Yeah, there's some funny stuff where we have a lot of posets and you like flip based off of whether you have varieties or ideals or corner sums or ASMs. But anyways, so one could say, okay, like these corner sums of ASMs were nice, but maybe we're like missing stuff. Maybe there's more like wild rank conditions that we could put down and we could give some like random rank table. Like maybe it has infinity, maybe it has like 2.5, which we could round down to 2. But anyways, we could put down whatever random rank conditions we feel like. And so Fulton showed that this thing is irreducible if and only if we have the rank matrix of a partial permutation. And up to affine factors, any random list of rank constraints you could put down is just an alternating sign matrix variety. So ASMs, they classify this family of varieties that Fulton was studying. So that's like all there is when we're defining things by ranks in this way, by these northwest sort of conditions. So again, ASMs were living inside of this geometry before people knew that they were there, and they were just always there. Yeah. So yeah, sort of one of the themes is they just keep popping up in Schubert calculus, and like, yeah, they were there. Okay, so yeah, I want to tell you a little bit about how that statement goes without getting into too many details. But what I've drawn here is sort of basically Lascoux's Rothe diagram of an ASM. And Lascaux didn't really draw the things being struck out in this way, but he defined the diagram. But what else does this look like? It's a bumpless pipe dream, right? Okay, I'm just drawing it like this because of maybe history, or maybe to tell you I'm not trying to write down a Schubert polynomial, but I'm trying to get rank information about my ASM. But anyways, I want to point out that this picture gives you a very nice way to get the inversions of an ASM, which is something that we care about when we're doing various enumeration of ASMs by statistics. And so the inversion set, the sort of non-negative inversions are these blank tiles. And then the negative inversions are the -1s. And so you can read off the inversion statistics very efficiently from these diagrams. But what we do then in this geometric setting is we want to find what's called the essential cells. So we look at kind of the union of the blank tiles and the -1s in this picture. And the essential cells are the ones that have nothing immediately to their right and immediately below them in that subset. So here, there's like no blank tiles or -1s to the right and none below. So this yellow thing is an essential cell. This one, it's in what's called the Rotha diagram, but it's not an essential cell. It kind of, any rank condition it would have is implied by this one here. So this notion of essential set for ASMs is just a direct generalization of Fulton's essential set that he gave for matrix Schubert varieties. But the point of the essential set is instead of taking n² rank conditions, it's enough to carve out the ASM variety by just looking at the essential rank conditions. So I could tell you, give me the things where this is rank at most 0, and this is rank at most 2, and that would be enough to determine the whole ASM variety. And you can also go back to Lascaux and Schutzenberger's sort of structure theorem about this poset of ASMs, where they showed that by Grassmannian permutations, those who are Grassmannian, but their inverse is also Grassmannian. The fastest way to see it in the diagram is that their Rotha diagram is a single rectangle. The bigrassmannians are the join irreducibles in this poset of ASMs. And that means that everything can be uniquely realized as an antichain of bigrassmannians. And so to get the correct antichain, you just look for the bigrassmannians that have the essential box at the same position, and they match the rank of the corner sum at that position. So this one has 2 different bigrassmannians in this thing. And it turns out the join operation on the poset is the same as intersection of the varieties. Okay, so that gives you, again, a way to see that those are just the conditions that matter. I wanted to tell you about another poset structure on ASMs that I think is less well known, but is giving us some interesting information about the geometry of these varieties. So building on work of Terwilliger, Hammacher and Reiner, they defined a notion of weak order, so weak Bruhat order on alternating sign matrices. So it's a different poset from the strong order poset. And when you restrict to looking at just permutations, it's the same as the ordinary notion of weak order on permutations, where you're looking at how can I apply simple transpositions and go up or down in this poset. So this weak order thing, again, I drew 3x3s. It looks just like ordinary weak order over here, but then there's this extra ASM. This covers these 2 things. And I'm not going to give you the exact definition of weak order. It's some sort of like toggling on the corner sum matrix where you just take a row and you keep toggling it bigger until you can't make anything bigger, and then you look at what you got. So that is essentially the definition, but too fast to process. But yeah, if you want more details, I'm happy to talk after. And I just wanted to tell you, like, one sort of enumerative mystery is that, well, in ordinary weak order and of permutations, it's a lattice, but this definitely fails to be a lattice. There could be a lot of maximal elements. And I think this data is due to Hammacher and Reiner. They computed the number of top elements in ASMN. And so here I've listed out the top elements in 4x4 matrices. And it turns out that something is maximal in this order if and only if it has an essential box in every single row up until the the last row can't ever have an essential box. But yeah, so this sequence, at least last I checked, wasn't in the OEIS, so who knows what it is. But I don't know, like this all started with a nice sequence of numbers. This is not as nice of a sequence as the ASM numbers, but here's a sequence that has a little mystery with it. So yeah, what does this count? Yes, yes. Great, great. Okay. Top ASMs, 80 years of top ASMs. Okay. So, but I wanted to point out that the weak order is very, very compatible with the geometry of ASM varieties, and it actually helps us understand a bit about this geometry. So when you're kind of going down by applying a weak order operator on row I, then the ASM variety that you get is just what you get by taking the union component-wise of the things in the perm set and applying this operator. So you just kind of component-wise look at what the weak order does, shove that all down. You might have some redundancies and you throw away the extra stuff, and then you find your perm set living inside of there. So this gives you a nice recursive way to think about perm sets, whereas before, to compute it, you had to kind of take your ASM and then you had to go hunting in the ASM lattice, and you might have to pass through a lot of permutations or a lot of ASMs to find your minimal permutations. This also kind of tells you that the components, the number of components decreases weakly as you go down in weak order. So things sort of get less complicated as you go down. And then also you can think about saturated chains in weak order intervals from your favorite ASM down to the identity. You can read off information like what is the codimension, which the codimension of an ASM, you can of course compute it by looking at the perm set and looking at sort of the minimum Coxeter length of the permutations in there. Because for matrix Schubert varieties, codimension is just the inversion number of the permutation. But for these alternating sign matrix varieties, I don't know of just a simple statistic on ASMs that computes this codimension. This is another thing where I've gone to find stat and I've asked like, what is it? And I've asked it to compose maybe too many maps and greedily used up resources and nothing is ever found. So it's not just the inversion number of the ASMs. I don't think the inversion number even bounds it in any sensible way. So anyways, you can find it by looking for a minimum length saturated chain in this weak order. And you can actually read off the perm set by looking among all these chains, what permutations do you get, and potentially throwing away some irrelevant chains that are implied by other ones. So this is something that's like not maybe the most practical in general because you can get a lot of different chains as you get something that goes up higher and higher in weak order. But it's a different way to think about this permutation set and understand this geometry. Okay, I had a bit about Grosvenor geometry. I'm starting to get to yeah, okay, I'll say a few minutes. I'll do the slides really fast and then that'll be okay, right? That's always how the end of talks work. Okay, so what we can do is going kind of back to matrix Schubert varieties. You can define a Schubert determinantal ideal, which is just the ideal that's really carving out that matrix Schubert variety. And so you're just taking these minors of the specified sizes. Here, I'm just using Fulton's essential set, and that's enough minors. And you get this sort of object here. And this, again, is just the vanishing locus of the matrix Schubert, or the matrix Schubert variety. Sorry, I should have said vanishing locus of Schubert determinantal ideals is the matrix Schubert variety. But the way that these things really connect to Schubert calculus world is they're sort of affine lifts of these Schubert varieties that we're living down in the flag variety. So I just wanted to point out kind of that connection to the piece of the story that we saw before with our Schubert calculus land. But Fulton showed that these are like the right generating set and that the ideal is prime. And so it's like a very nice ideal. So I'm going to just like play a game, and I'm going to do what's called a Grosvenor degeneration. So I'm, again, not giving you enough details, but I'm going to fix what's called a diagonal term order, where I can, if I take a matrix minor, the biggest term in that matrix is the product of the things on the antidiagonal. And so I can use this sort of thing to do some sort of Grosvenor degeneration, where I want to look at the ideal that's formed by the lead terms of all the things in my ideal. Here, it was enough to take this generating set. In general, you want to find something called a Grosvenor basis to do this. But I can take this, I can take a prime decomposition, and the primes that I get are corresponding to bumpless pipe dreams. So when I do this funny geometric degeneration, I just want to point out that in the limit, there's ASMs just waiting. So ASMs are showing up not only as like geometric objects or as helping us write down the polynomials, but they're showing up to help us write down the polynomials because of this degeneration morally. So they were hiding in this aspect of the geometry all along as well. And then indeed, if you don't go all the way to do an initial ideal, if you just sort of take one step, you really get that this one-step degeneration is just sort of a mild adaptation of a determinantal ideal intersected with this ideal for the, so of a Schubert determinantal ideal intersected with the ideal for an ASM variety. So the ASM varieties are telling you about these one-step degenerations. And this is sort of, I'm not telling you enough for you to understand this, but there's this thing called the transition recurrence that works on geometry and polynomials and the combinatorial objects all together in harmony. So it's a recurrence on literal ASMs as well as polynomials and geometric objects. And my theorem with Patricia Klein is that if you take whatever intersection of Schubert determinantal ideals of the same codimension, then when you look for certain diagonal term orders, the components in the limit are being labeled by these bumpless pipe dreams with some sort of notion of multiplicity. Again, bumpless pipe dreams, they're ASMs. And intersections of these things are sometimes ASM varieties. This one doesn't happen to be an ASM variety, but it highlights the notion of multiplicity in a reasonable way with a small example. So here I take this intersection and I get sort of just this single thing. When I degenerate, I get sort of a squared term, which is telling me about the multiplicity. And so this is saying I should be seeing two copies of something with this weight and one copy over here of something with this weight. And I'm seeing different bumpless pipe dreams to tell me about this multiplicity because they have the same blank tiles. Okay. And yeah, so that's about where I wanted to stop. So thank you.